Welcome back to another lecture. In this lecture, we're going to design one of these interior pre-stressed concrete composite beam. Now, the dimension, let me actually bring up this. So basically the beam, the deck slab is about 7 inches. The span is about 80 feet long. And we're going to use AASHTO PCI girder. And the spacing between is 725. The width is 35.5, and then we're going to go ahead and just design it. So step one is going to be, we're going to find out the design criteria. Our design criteria is for this beam, we're going to use, let me bring this up here so you can see them. And this Excel sheet, what I have is the barrier where it's going to be 0.39 kip per foot. And the concrete strength is going to be 5 KSI for the deck. For the girder, we use 5 KSI, but normally we don't use 5 KSI for the girder. We use about 8,000. So let's go with 5 for now, and then we're going to find out why it was not good enough. So anyway, so we're going to use 5 for that too. And then future wear and surface 25 pounds per square foot. And span length is 75 feet, spacing 7.25. Our concrete is 150 pounds per cubic feet concrete. And a specified tensile strength for the pre-stressing steel is about 270 KSI. Our deck is 7 inch and 2 inch of wear and a half wearing course. All right, so that's that. Let's go ahead, proceed to the next step. So our next step is going to be step 2. And let's compute the effective length. And BFF is basically, it's going to be your turbo tree width. We talked about this before, how much this beam is going to support. It's going to support this much of this concrete right here, okay? And this is a halfway between here and there, and halfway between here and there, which basically becomes 7.25 feet. So that's a 7.25 feet. And let's go to step number 3. It's going good. I wish everything was good like that. Step number 3 is going to be compute composite section. Compute composite section. Step 3, we're going to go ahead and compute the composite section. One of the things is, let me bring this up. I can explain for my Excel sheet here. We're going to find out, so make an Excel sheet for yourself right here and have the bisection just like what I have here. And in here, we're going to have the deck slab, which is basically right here, 7 inch by 87 inch. That's my area. And then my 49.5 is basically from bottom here, which is from bottom right here, up to here is 45 inches, plus 1 inch of hunch, that's 46, and plus 7 divided by 2, that makes it 49.5. And the rest is explanatory. Your I is 1 over 12 of BH cubed, you know that. Then the composite girder, I have already calculated it. Remember, this bottom, see, is bigger than the top. The bottom here is 22 inches. The top is 16 inches. So the center of gravity for this shape, which already been calculated, it's about 20.27 inches, 20.27 inches from the bottom to the center, and that's where that Y come from. And you put everything together, we can calculate the moment inertia, and then we can calculate the center of gravity for the composite shape, which comes out to 35.5. Anyway, so that's step number 3. Let me get rid of this, and we can proceed to step number 4. So step number 4, it's going to be calculate the dead load bending moment. Compute dead load bending moment. And we're going to start out with the dead load of the slab or the deck and that comes out. That was a 7-inch deck. So that basically is we looking at the composite section part of this, which is let me draw that. Okay, so we're gonna go ahead and calculate the dead load bending moment. We're gonna find out how much it's gonna weigh first. So it's gonna, this is a 7.25, and we said that that is right here is 7.25 feet, and this is a 7 inches and 150-pound concrete. So I'm gonna have 7.25 multiplied by 7 divided by 12, and then time 150 pound per cubic feet. Pound per cubic feet, we can say 0.15 kip per cubic feet. And that's per 1 foot section. So that's going to come out to 0.634 kip per foot. Next, we're going to go ahead and calculate the dead load of the hunch. And that's a 1-inch concrete. So the hunch right here, this distance right here, I didn't do the hunch right there, so let me kind of cut this out a little bit. There, make this a little bit shorter. And this is the hunch, say this is a 1 inch. So that's going to be 1 inch. And this is basically right here, that's a 16-inch, this width right here. And you can see that in the picture above too. So that's a 16-inch. So I got 16-inch divided by 12 time 1 inch divided by 12, and then time 0.15 kip per, and that's come out to 0.017 kip per foot. So the next thing we're going to do is that the girder itself, dead load of the girder. And this is this big hunk of concrete. And that's going to be the area of this whole thing is already pre-calculated, as given, is 560 inch square. And multiply that by, divide that by 144, let's make it foot square. And then multiply it by 150 pound concrete. And that gives me about 0.538. 0.538 kip per foot. So now we did that, then we have the barrier. We're going to calculate the dead load of the barrier. Dead load barrier. And that was given at the design criteria that we had in the Excel sheet. You can go back, look at that. That was given as a 0.39 kip per foot. So you didn't have to really figure it out. And then we have two sides, so it multiplied by two sides. Then we have 1, 2, 3, 4, 5 girder, so divided by 5, and that's going to come out to 0.157. 0.157 kip per foot. So now that's done. Then we have the wearing surface that we're going to go ahead and put here. Again, from the design criteria, the DL wearing surface is going to be, we said it was 2.5 inches. Divided by 12 and multiplied by this distance is 35.5 from one end to the other end, so I say 35.5, and let's take out these from here to here, so it's going to be 2 times 175 minus 2 times 1.75, and that should come out to wait a minute, got to multiply by 0.15, 150 pound concrete. That's a kip per cubic feet. And the answer should come out to 0.2 kip per foot. And I'm running out of room right here. So keep these calculated. I just erased the board. Now that we have calculated all the dead load per kip foot, so we're going to find the moment. And we know moment for something that is when you have a beam is distributed load, we have M is equal W L squared divided by 8. And our first one is going to be M moment of the deck. So M for the deck was, we had the load, which I erased down here. It was 0.634, and we got to add the 0.1017, and 0.017 is for the hunch itself. So the deck plus the hunch, 0.017. And then that's your W, and L was, we said that the length of the bridge beam is going to be 75 feet. So times 75 feet squared and divided by 8, and that comes out to 457 point. So I'm going to go ahead, write this down here in this corner. M dead load comes out to 450, that's not a good 57.7 kip foot. All right, then the next thing I'm going to calculate is the moment for the girder. So M girder is equal, the load came out to 0.583 times W, that's W times 75 squared, and divided by 8, it comes out to 409.9 kip foot. 409.9 kip foot. So I'm going to go ahead and write down here, because I need them later. M girder is equal 409.9 kip foot. Okay. The next one we're going to find is the barrier. So I'm going to go moment for the barrier. The barrier load came out to be 0.157 times L squared divided by 8, and that come out to 110.4 kip foot. Let's write that down over here. So we have that one too. M barrier came out to be 110.4 kip foot. Okay. So now we have an M wearing surface. The moment of the wearing surface come out to, the load came out for 0.2. Did it come out to 0.2? Yep. So that's a 0.2 times 75 squared divided by 8, and I end up with 140.6. 140.6 kip foot. Remember, that's the dead load of the whole thing. The dead load of all this come out to the total. So the total of dead load is going to come out M dead load. And I'm going to write down the M dead load. Total, if I add all these, comes out to 1118.6 kip foot. We need that. Okay, so now that's one step. Let's gonna go move on to the next step. That's step number 5. We're going to compute the life load distribution factor. Distribution factor. So let's get to work, and we're going to go ahead. I got to bring up the from AASHTO. We done this before from the other problem. 4.6.2.2.1, the longitudinal stiffness factor Kg is equal N time I plus A time Eg squared. Now, our N is module elasticity of the concrete over the deck, EC slab or deck, divided by the EC of the beam. In the design criteria, we said they're both 5,000, which is, in real life, you don't do that. This be 5,000, this be probably 8,000. But let's go with what we said. So that going to comes out to 5,000 each. And then the our E is, let me bring up calculated EG. Our EG is from here to here is 45 inches. So I got 45 inches. And then let's take off this much, which is 20 minus 20.27. Then I got plus 1 inch of hunch. And then plus halfway through there, which is plus 7 inch divided by 2. And that should give me 20 something, 29.23, 29.23. And so this came out to 1. And I became, for the girder, which we had in the spreadsheet, we already know that's 125, 390, 125, 390 inch by power 4 plus area. Area was 560. This is for the girder. And time EG. And EG we just calculated to be 29.23 time 29.23, square that, and Kg comes out to 603,900. 603,900. That's a 9. Okay. Now we have that. Let me erase the board here. We need this for distribution factor. Okay. From AASHTO table 4.6.2.B1, we can say for 2 more or design lane, our distribution factor is going to come out to 0.075 and time plus S divided by 9.5 by power of 0.6 time S divided by L by power of 0.2 time Kg divided by 12 time L T S cubic. And that comes up, that's by 0.1. So I plug that in, it's going to come out to 0.075 plus our S was 7.25 divided by 9.5 by power 0.6 times 7.25 divided by L was 75 feet by power 0.2, and then Kg came out a big number of, what was that? 603,900. Divide that by 12 times 75 time 7 divided by power of 3. And that comes out to 0.644. So that's our distribution factor. Okay, now we calculated the life load distribution factor. We're going to calculate the step number 6 would be calculate life load, say step 6, compute life load moment. We talked about this before, and there's a video on it. We even did it in robot. We said when we have a HL93 loading, that means you have a 32 kips, and 14 feet later you have another 32 kip axle, and then you have another 8 kip. We said the maximum moment, and we used the structural analysis. We ran the vehicle all the way from one end to the other end, and we did the influence line, and we found out if the center tire is about 2 feet 4 inches away from the center line, that's where you get the maximum moment. So that's why we have that there. A lot of time you see in a lot of books what they do, they make a calculation. They just put this in the center line. They don't bother that. But it comes out very close. So we know that's very close. So let's go ahead. Before we're going to calculate the maximum moment, we're going to calculate the reaction forces for this type of load. I'm going to go ahead and take a moment about point A, which is right here. So a summation moment about point A is equal 0. Counterclockwise is positive. And I'm going to have start from here. RB first is going to go times 75. Then minus the first one is going to be a 32. And that came out to that distance. You can figure easily out. It's going to become basically 11.67 plus 75 divided by 2. And then we have the this one minus 32 feet time. That's just halfway. It's going to be 75 divided by 2. And take out the 2 feet 4 inches, which is minus 2.33. Then I'm going to also have minus 8 feet time. That little distance came out to, if you calculate it, it comes out to, it's going to be, actually, we can just calculate it. 14 plus 2.33. Minus I got that backward. So I got to say 75 divided by 2 minus 14 minus 2.33. And the whole thing we're going to find out, the RB comes out to 38.24 kips. From summation FOY is equal 0. Going up is positive. Our RA comes out to basically, we have 38.24 minus 32 minus 32 minus 8. And then it's going to be plus RB. Plus RA, whatever. I got it. So RA kind of come out to 33.7 kip. So now we have that. Next we're going to calculate the moment. And the moment for the life load is going to come out to M. It's going to come out to, well, no, wait a minute. I'm not done. I'm getting ahead of myself. We're going to calculate the maximum moment. How we're going to do this, we're going to go ahead and take the center wheel and cut the hole right there. So I'm going to come in right here and cut it right there. And this is the 32 kip load. Then I'm going to have the 8 kip load right here, which is about 14 feet away. Let me not mix those up. And then I'm going to have the reaction force right here. And that RA came out to 33.7. So now I got this load, and then I'm going to cut it. I'm going to have to fix it with shear, moment, and this. But I'm looking for this moment right here. So if I take a moment about this point, and this point was the distance right here, it's going to be 75 divided by 2, which is 37.5, minus 2 feet 4 inches, which is 2.33. And that's going to be distance. which comes out to 3517, I believe. Double check my number. So now I have that. I'm going to find this maximum moment. So take a moment about this point. It's going to be 33 times 3517. And then we have the 8 kip going to be time 14. Minus 8 times 14. And that will give me that moment. And of course plus m, because taking a moment here. So m max going to come out to 1073 kip foot. 1073 kip foot. And we always said that when we do a live load, there's 3 ways we got to do it. We got to do this, and then we got to do the military load in tandem, which is 25 kip on each side. And then there's whatever which one control, and plus the 640 pound lane load. So let me erase this, and we're going to go to the other one. We said this was, when we do HL93, then we're going to do tandem. And the tandem is right here. Let's figure out what is the moment come out for the tandem. Because that's a tandem and it's easy, we know it's a 25-25, so my reaction is going to become 25 kip here and 25 kip there, so that's easy. And let's take a moment to calculate the maximum moment and say it's going to be under the 25 kip, and I have 25 here. And if I do that, so cut this beam, I'm going to have shear coming, moment coming, and actual force. I care about the moment. And this distance comes out to 37.5 minus 2 feet. It makes it 35.5 feet. And so my moment comes out basically, moment for the tandem is equal 25 times 35.5. That's it. There's nothing else in a way. And really that comes out to 877. And remember, I just erased the board. And moment for the other one came out to 1,000 something. So that one controls. That one was 1,073. So that one controls. The moment for this one came out to 1,073. That controls, because it's bigger than this one. In addition to this, so we're going to find out which one is maximum. Then we're going to find out the design lane load, which is 640 pound. Basically, you have your beam right here, and you got to add 640 pound per foot, or 0.64 kip per foot. And the maximum moment for this one is going to come out. We know that it is W L squared divided by 8, which is a 0.64 times 75 squared divided by 8, and that comes out to 450 kip foot. Now, when we do the life moment, we do HL93 and a tandem, whatever which one is bigger, which was this one. Then we do the lane load, which is this one. Now the moment for how this going to become the distribution factor plus, this going to be MLL plus IM. And that's going to be this distribution factor multiplied by all that stuff, which is going to be 0.644 time. Remember, we talked about this. You have to have a 33% factor. What was that? 0.33 times 1073, which was for this one right here, and plus 450. Dynamic load factor right here, and that comes out to 1208 0.8 kip foot. So now we're going to go ahead, we need that number 2, and we're going to say MLL plus IM came out to 1208.8 kip foot. Okay. So we're going to go ahead and calculate the stress at the top of the girder. So we want to find the stress right here at the top of the girder here. Okay. Now that top of the girder, the stress top of the girder, let's call it top girder. This is non-composite. So if a non-composite due to the deck load, okay? So due to the deck load, it's going to be equal. We said the deck moment came out to 457.7. 457.7. That was a foot kip. Let's make it inch kip. So multiply by 12, and then times C. C is the distance from the neutral axis to the top. In this case, it's from here to there, so which is 45 inch from here to here minus this portion, minus 20.27. And then divided by the moment inertia of the girder came out to be 125.93. 930. No, I gotta get it right. 390. 390, and that comes out to a 1.08 KSI. So now we have that. And then we're going to go ahead and find the type 3 girder, which is right here, the girder itself. So this was for the due to the deck. Now due to the girder itself, it's going to be F at top, come out to, the load came out to with 409 for the moment, 409.9 kip foot, multiply that by 12 again, make it inch, and the distance for the girder is going to be 45 inches. Remember we said it's the same thing. It's the same distance over there. So 45 minus 20.27, divide that by the same area, same moment inertia, 125,390, and that will give me a 0.97 kip KSI. So now that was for non-composite. Now we're going to go to composite. So for composite, we're going to have, we're going to have to find our neutral axis. Neutral, so the neutral axis was someplace around here. Remember, we said this was NA, or center of gravity of the, actually we call it center of gravity of both of them for a composite. Let's call the center of gravity of composite. And that came out to be, from the Excel sheet, it came out to be 35 inches, I believe, 35.5. So that was from here to here was 35.5 inch. And we have that. We're going to go ahead and calculate this for composite. We're going to find out the F for LL plus IM, or sigma, whatever what you call it. We said our moment came out to 1208.8. Let's multiply by 12. And then we have the moment inertia is going to, the center of gravity is going to be between here and the top. So that means 45 minus 35.5. 45 minus 35.5, and divided by the moment inertia for the composite beam, which we calculated from the Excel sheet, came out to become 377,102. So this will give me the 0.365 KSI. And then we had one for the barrier, and that comes out to 110.4 times 12 times the distance going to be the same thing, with this comes out to 9.5. So that's where it comes from, 9.5, and divide that by same thing, 377,102, and that will give me 0.033 KSI. Then I'm going to do the wearing course. So F's wearing course comes out to, I wrote it down, it was 140.6 times 12 times 9.5 divided by the same thing over here, 377,102, and that will give me 0.042 KSI. So the total, all this comes out to, all of them, so 1, 2, almost to 2.49 KSI. I need those numbers. Okay, so I erased the board and I put the F at top that we had, came out to 2.49 KSI. Now we're going to go to step number 8. We're going to compute the stress at the bottom of the girder. We're going to do the same thing. We're going to go non-composite. First, we're going to go do to the deck, which is going to be 457.7 and times 12, and then times C. Our C is going to be same as before C, which was 20.77, and divided by the girder moment inertia, because this is a non-composite. So it'd be 125,390, and that comes out to 0.89 KSI. Then we're going to have due to the girder itself, which is a type 3 AASHTO. So F at bottom comes out to, and that moment was 409.9 multiplied by 12. There was a kip foot, make it a kip inch, and then time 20.77. divided by the same thing over here, which is moment inertia, and that will give me 0.81 KSI. Now, the next thing I want to do is go to the composite. Let's go to a composite section for here. And due to the deck again, no, sorry. It has to be the life load of F I L L plus I M, and for the bottom it's going to come out to 1,208.8 times 12, and let's multiply that by the distance between that. It's just like as before, what came out to from the bottom to here, we said is 35.5 inches. 35.5, and divide that by the composite moment inertia, which was 377,000 and a change, which was 102. And that comes out to 1.36 KSI. So now the next thing we have is the for the barrier. And that's going to be 110.4 times 12 times, same thing here, 35.5 divided by the same moment inertia, and that'll give me 0.124 KSI. Then we're going to do one for the wearing surface. I think it was 140.6 times 12 times 35.5 divided by the same, and that give me a 0.159 KSI, and total gonna come out to 3.34 KSI. So I'm gonna say F of bottom comes out to 3.4 KSI. Was it 4? No, I was right. 3.34. 3.34. There. So we just finished step number 8. So we put down this bottom stress 3.34 KSI. We're going to go move to step number 9, which is compute initial pre-stressing force. Before I do that, I got to find out what's the distance between the center of my pre-stress to the center of the girder is going to be, which we call this E. And that E, it's going to be basically, that E is going to be 20.27 minus 3.5 inches. And that comes out to 16, I have it down here someplace, 16.77. And then we're going to calculate the radius of gyration. So R squared is equal I divided by area. And our I was 125,390. Divide that by the area was 560, I believe I'm correct. 560. So that's gonna come out to 223.9 inch squared. And you really, for this section from now on, study, read AASHTO 5.91 to 5.9.3, a lot of good stuff there. All the formula and stuff is in there. So we want to find the effective, from the AASHTO, we want to find the effective pre-stressing force, PF, and that's going to be basically the our F of bottom time the area, and divide that by the 1 plus E time Y bottom, and Y bottom is this basically right here, 2027, and divide that by R squared. So now that comes out to 3.34 KSI. Area was 560, and time 1 plus, we have 16.77. Y bottom was 20. That's going to be multiplied by 20.27, 20.27, and divide the whole thing by 3.9. So that comes out to 745 kip. Okay, so per AASHTO 5.9, 5.4, we have the pre-stressing immediately prior to transfer. It's going to be 75% of the tension that we have for the pre-strand, which we talked about at the beginning, was 270 KSI. So we're going to say our F of P, it's going to be 0.75 times F of U, and that's going to be F of PU, and this should be F of PBT, and that comes out to 0.75, and that was 270. So we're going to end up with 202.5 KSI. And keep that in mind. And so when we have a loss, we got, let me bring another PowerPoint right here. Okay, take a look at this. So we go for pre-stressed concrete member. Some of the initial pre-stress is at the beginning is lost because of the different reason, and some of those are instantaneous loss, the way they set the anchorage or friction or elastic shoring, and also over time because of the creep and just wear and tear, relaxation, you're going to lose some of this pre-stressing. And here's the interesting thing. A report by a joint committee of ASCE and ACI suggested unless precise data is available, steel stress losses may be assumed 35 KSI for pretensioning, which in our case, and 25 for pretensioning. And then you might see another table from an older books or AASHTO. You might say 30 actually for pretensioning. So anyway, so we're going to go ahead and use a 35 based on this recommendation of loss. Let me bring back my PowerPoint now so you can see me. Oops. Yeah. And go to the next page of my calculation. So we had 202.5. We're going to say, all right, our FAE 202.5 minus 35 KSI that recommended, and they're going to come out to 167.5 KSI. And assume losses due to the elastic shortening. Remember we said, so let's assume losses to elastic shortening. We're going to assume for that, and we're going to come back and confirm it. Elastic shoring be 13 KSI, 13 to 15 KSI. Let's say there's 13 for now. And then we're going to say, okay, we have 35. We said 35 someplace. And then we say 35 minus 13, that will give us 22 KSI. So now we're going to have that, and we're going to say our PF comes out to PF plus loss due to the transfer loss due to transfer, multiply that by the area, and that comes out to we didn't calculate the area, so let's calculate the area first. Where did I do that? The area, I'm going to use a different color so we can see it better. This is good. The area, APS, it's going to be PF divided by FAE. So we had 745 kip and divided by KSI, so the inch square come on top, it become the area. And we said the loss, everything came out to 167.5, 167.5. So my area comes out to 4.44 inch square. Now that's going to come in right here. Okay, so now it's going to have, what we're going to have here, it's going to be 745 plus 22, and that 22, that's not a good looking 22. Let me write that again. This can make a mess sometimes. Plus 22, which is this, and then it's going to be multiplied by the area, 4.44. 444. And that comes out to 842.7. Now, let's go ahead and calculate this, that's a kip, in different ways. See if you're going to come up closer to that number. I'm going to keep that one right here. I'm going to erase up here. But to just confirm this, we said, we guessed that 13 KSI, we said, which I erased, 35 minus 13 came out to 22. This way we can find 21, and instead of 21, put 21 here, we come out close number. So we're just going to use this, and that was another way if you're using the AASHTO formula. So let me erase that. We're going to go ahead and proceed to the next step. Okay, so we're going to move to next step, which is a step 10. Let me bring my PowerPoint up here as I explain this. So in step 10, we're going to go ahead calculate the stresses at 3 different times. 1, when the beam is pre-stressed. 2, the slab is placed, the deck is slabbed. And then finally, under the design loading condition. Now, one thing you got to remember here, at the time of pre-stressing, only the girder dead load is calculated. And the maximum compression is checked using service limit 1, and the maximum tension is checked using service limit 3. So, okay, let's get to work and work on this step. We're going to go ahead, first calculate, let's use this color here. If we know from the AASHTO, we have all those equations that I told you to read. F is equal P F divided by area, and then it's going to be, this is basically our P1 time 1 plus or minus EY divided by R squared. Of course, you could have a Y bottom or Y top, depending on what we're looking at. And then we have, so let's just write this out. I'm going to say F is equal P1 divided by A time 1 plus EY divided by, that's YT, YT top divided by R squared, and then we have the other one is going to be F is equal, that was F is equal P1 divided by A time 1 plus E Y of bottom divided by R squared. And 1 plus EY top divided by R squared, that basically going to come out to become 1 plus 16.77. Y came out to 24.73 from the Excel chart we had, and divide that, and the shape we have right there, I'm going to put on the board. And it's going to be plus divided by R squared came out to 3.91, so this will give me about 0.85, and so one of my equations on top there is going to become P1 divided by 8 times 0.85, and the other one is going to come out to 1 plus 16.77 times Y bottom comes out to 20.27, 20.27, and divide by R squared. And so, okay, this is a minus actually. That's so 1 plus that number, and that's going to come out to 0.85. 1 time plus this, r squared, which is the same thing. That comes out to 252. So this is going to come out F is equal P1 divided by A times 2.52. And we're going to go ahead and one thing I didn't wrote down here from previous step that we calculated, it was our F our P1 should have came out to, we had it calculated down here, was 805.9. No, we called it F or P, doesn't matter, same thing. So now we have that. Let me erase this. So now our F at top is, this is the equation for it. F at bottom, that's the equation for it. We just calculated this right here. And these F at time, remember in step number 8, we calculate those individual, and then we just put the total up here. So we're going to have to use the individual based on what we're doing there. All right, so let's go ahead and work. We're going to go ahead and say first, at the time of transfer, at time of transfer, we're going to have F is equal, and that's got to be 0.85 multiplied by 805.9. Okay, and that's going to divide by area 560. Then minus, if you go back to step 8, minus 0.97. Check that out. That's where we had that from. And of course, that's going to be this is going to be negative because we're doing it at the time of the transfer, and that's going to be a tension. So that's going to be 0.25 KSI in tension. So this right here, we're going to be top flange, at the top of the flange. So now the one was the time of transfer, and the other one is going to be at the time of the slab in place. Concrete deck slab in place when they put them in there. Okay, so our F is going to come out to, can you see that? Yeah, you can see it. F is equal, and that's going to come out to minus 0.85 times minus 805.9 divided by 560, and then we're going to have to take out minus, because it's in place, it's going to be this combination plus 108. Go back to step 8 to see what they are, and that's going to come out to minus 0.826. Minus 0.826, that means in compression. So we say plus is a tension, negative is in a compression. And then it's the same here at, we got to do service 1 design. Service 1 design load. So now we're going to have F is equal minus 8.5 It should be, I guess there is minus up there. I forgot to put a minus there. Minus times minus is positive. Okay. So minus 0.85 times minus 805.9 divided by 560 minus 249, which was the total, 249, and that gave us minus 127. Minus 127 KSI, and that's in compression because it's negative. So now that was for the top. Let's do the bottom girder. And let's do that with a different color. We have the bottom girder, again, at the time of the transfer. I'll write these down. At, can you see that? Time of transfer. So that's going to be basically that equation there. So F is equal 2.52 time P was negative 805 time minus 805.9 divided by 560 and plus 0.81. And that gave us minus 2.8 KSI. That's in compression. The next one we want to do is the same thing at the time, deck slab in place. So that's going to give me F is equal 2.52 time minus 805.9 divided by 560, and it's going to be plus those two combined, which was 0.89 plus 0.81. I think that's all plus. That's a negative, that's correct. And I got minus 195. And that's in compression, KSI. Okay, so the next one we're going to do at service level. One. So that's going to be F is equal. We have 2.52 time minus 805.9 by 560, and that's going to be plus the total, which was 334. And that's a minus 0.288 KSI in compression. Now you look, this is compression, 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 compression. The only time we have is a tension is up here. So we're going to check the tension for these are maximum compression going to be checked. Those two are going to be checked differently, like we talked about in the slides. So let's continue. Let me erase all this number. So, all right. So now we're going to go to the next step, step 11. We're going to go ahead and do a stress limit check, as we talked about it in, before. So I'm going to go ahead do the per AASHTO. If you look at the AASHTO 5.9.4.2.1-1, and we're going to get F prime C is equal to compressive stress, which is compression, which we calculated to be, I erased it, divided by the 0.6, and just like what we have in AASHTO, and that came out to 2.8 KSI. We said tension was positive, compression was negative, So 0.6, and this will give us 4.67 KSI. So now, we can use, we said at beginning at the, when we had the design criteria, we said our concrete was 5,000 PSI. So 4,000 PSI, if this makes it okay. The deck was 5,000, and we said the prestressed was 5,000. It's pretty close. Normally we do about 7,000, 8,000. So let's just say go with the problem for now. The compression stress passed. Let's find out if we can find the tension one. So for AASHTO, same thing right there, and then AASHTO we can find out the tensional stress for pre-tensioning member, the tensional stress, and that's going to be tension. This was compression. Now tension. It's going to be, we have 0.0948 times F prime C, and that come out to, it says 0.2 KSI. And in our case, we used 5, so we said 0.0948 with 5 KSI. That will give us 0.211, which based on an AASHTO spec, that's more than 0.25, which is no good. And therefore, we're going to change that to maybe like a 7,000 PSI. If we go 7,000 PSI for this concrete here, we're going to have, let's put a number here for 7,000, 0.0948 times 7. And that comes out to 0.25, and that checks out with that, so that will check out 7,000 minimum. But there's another way we can fix that. We say because this is not going to pass the tension, we just add more rebar on top. We get to that in a minute. So our F prime C, we're going to say we have going to be LL stress, stress to the life load, plus pre-tensioning loss, and divide that by 0.6 per AASHTO, and we're going to come out to 1.36. And we calculated in the previous steps, plus 0.124 plus 0.159. If you go back to your notes, you find out where those come from. Divide by 6, and they're going to give us 2.7, which is less than, we said 7 or 5 we're going to use, and that's going to check out it's okay. So allowable, next one we're going to check out is the allowable service 3 load. So we said at the beginning for compression we're going to use go service 1. For tension we're going to use service 3 load. So service 3 load per spec is going to be 0.19 square root of F prime C, and that comes out to 0.19. If we convert this to 7,000, be careful when we do this 7,000. At the beginning we used 5,000. So our N came out 1. But if we had this 7,000, then our N is going to be different. But for now, we're going to stay with that. And normally, we don't use 5,000 PSI for these, just for the example to show it here why it didn't work out. So it's 0.9 times, say we use 7,000 PSI, and that's going to come out to 0.5, which is more than 0.288, and that's going to check out. So I'm going to erase this. We're going to move to the next step. We're going to go to step 12. And step 12, let me see if I can bring this up. step 12, we're going to go ahead and do the draping for the tendon. Now, normally, if we had time, we can do a spread Excel sheet. We go ahead every 1/10, and we can go ahead and do this. But for this exercise, because it's so long, let's go ahead, let's do it at 1/3 for now, and we're going to calculate that. Let me bring this back down, and we can get back to work. That's not what I want to do. There we go. So we're going to go ahead and calculate the maximum moment, and max at different x, not at the, which is wx divided by 2 times L minus x in that situation that we had, which is on the board. And so we're going to say x is 1/3 of L at those location. And then we have m is equal WL. If you pick up any steel book, it could tell you this formula divided by 9. And we're going to have, or any concrete book. So that was for at 1/3. And we know moment at the center line is WL squared divided by 8. So the ratio of these two is going to be WL squared divided by 9 over WL squared divided by 8, and that's going to become 8 over 9, basically, so 0.89. So if I have this right here, listen here, make this like that. Okay, and our center line is right here. We had 32 kip, 32 kip, and 8 kip. And we said this distance was 2 foot 4 inches, 2.3. And this whole thing is 75 feet. We know that. And these are 14, 14 between each set of wheel. And we have RA, RB. Let's call this A and call this B. And we're going to take a summation moment about point A is equal 0. So now we're going to have RB times 75 and minus 32 times 39.83 minus 32, we did this before also, times 2583, and then minus, where's about the 8 one? 8 feet, 8 kips times 11.83 equals 0, and therefore our RB came out to 29.27, and from summation FY, our RA come out to 4270.7 kip. Now to find the maximum moment, so I'm going to go ahead and do like this, cut it right where I want it, right underneath the 32 kip load. And if I do that, it's going to have, well, it's going to work. I'm going to have moment here, shear here, shear here. So I care about the moment. And in here we had the reaction came out to be, 42.7. And the 8 kips is right here someplace. Okay, so we're going to find out the moment. It's going to be, this length is going to be L divided by 3, which is 75, divided by 3, which is 25. and that's why actually 32 is not going to be here. 32 is going to be outside of here because it's going to fall someplace around here. That's 25. That's where we want to find the maximum moment. Remember, we said we're going to do the tendons at 1/3 of the way. So now we're going to find it right there. And let's get to work on that. So that's going to become M1/3. We're basically going to go ahead and take a moment about right that point. So it's going to be 42.7 time. This marker says I had enough. How about this marker? It's already ready to go. 42.7 times 25. And then minus 8 times, that's going to be 25 minus 11.83 because this distance is 11.83 equals 0. So plus m. So about m comes out to basically, m comes out to at 1/3, come out to 962 kip foot. So that was a moment at 1/3, but the moment at the center line, which is going to be basically, we did calculate it before, remember? I'm not going to do it now. Here is 111.8.6. No. Yeah. Either was, I think it was WL squared divided by that. So that came out to, the ratio is going to become 962 divided by 1118.6, and that's going to come out to 0.86. So this ratio and that ratio, there's really not much different, so we're just going to go ahead with that. So we're going to go ahead and move to step number 13. We just calculated the ratio became 0.89. That's what we're going to use in this step. So in here we're going to compute the stress at 1/3 of the span of the beam. Just like last time we did all those calculations at the time of transfer. So let's get to work, and we're going to go ahead. I'm going to make, there we go. So I'm going to say at the time of transfer, at time of transfer, we're going to have same equation we had from previous step, minus 0.85. And this is going to be basically for the top of the girder. So at the top of the girder, at the time of transfer, we're going to have minus 0.85, the same formula we had before, times the minus 805, which we had down there, 0.9, divided by the area, which was 560 this time. It's going to be minus. Remember with the last time we just had minus 0.97. It's going to be minus 0.97 times the ratio, which was 0.89. And that's going to become 0.36 tension, KSI in tension. That's our tension stress, kind of high. So now we're going to have at the time of slab in place, when we set the deck, okay? And so when we put that down, that's going to be minus, same thing, minus 0.85 times minus 805.9 divided by 560 times, minus 0.97 and plus the 1.08. Again, that's from previous step, these numbers, and time 0.89, and that will give us minus 0.6 KSI. That's in compression. So finally, we're going to go ahead and check the stress at the service design load. At service 1 DESI design load. And that's going to become same thing, minus 0.85 times minus 805.9 by 5 divided by 560 minus was 249, and yeah, times 0.89, and that is equal 1 KSI compression, which is negative anyway. We're just going to say for compression. That's what we have in there. So now we're going to go ahead and go to the bottom of that girder. And that's going to be bottom of girder. Let me use, that was pink. I use green here. And same thing. Oh, I need that again. At the time of basically same thing at time of transfer, you know what I mean. So it's going to be minus 0.85 times, no, it's not minus, it's the other equation for the top one. 2.54 times minus 805.9 divided by 560, that be going to be actually plus 0.81 times 0.89, and that gave me minus 2.9 KSI in compression. And then the next one is going to be at the time of slab in place. And it's going to be 2.54 times minus 805.9 divided by 560 times 0.89 plus 0.81 times 0.89, and that gave me about 2.14 KSI compression. So number could be negative in there. Then we have the at the time service, this time at service 3 design load. And that's going to be 2.54. Let me write different color here. Okay. 2.54 times minus 805.9 divided by 560 time. That's not a time here. That's, excuse me, that's a plus right there. So this is a plus also. 3.34 times 0.89. That was for the total load. So that gives us minus 0.667 in compression. So this is this step, and we checked. Then we're going to come back and check it later in this next step. All right, let's erase this, and I come back to you. 5.9. We're going to go ahead and check the concrete stress. We said the compressive stress divided by 0.6, and that came out to, I erased it, which was 2.4 was the one, divided by 0.6, and that gave me about 4.8. 4.8 is less than what we said it was 5,000 or 7,000, so less than, say, 7,000 PSI, and that's okay, so that checks out. And let's go ahead and check for, then we said we had the stress limits of the, I erased it, was the tension was 0.36. Remember I said it was high. So now 0.22, which we know is less than 0.36. So this is no good. Remember when we, in the previous step, I just erased the board. We said the tension was 0.36. And this is less than that, it's no good. So we got to add some rebar to these top to make up for it. And max tension for AASHTO 5.9.4. We're going to say 0.24 times F prime C, which became 2.4 times 7. In our case, it's going to be equal 0.63, which is more than 0.36 is okay. Now we have that. We want to compute the longitudinal steel at the top of the girder for reinforcement bond, but we got to find out where the plastic neutral axis is. So if I look at this right here, I'm not going to go ahead. I'm going to go ahead. Let me use a different color. Maybe I can use pink. Now, change my mind. I use this one. So if we have that we calculated this, the tension was equal 0.36, and so this is going to come down like that. And our compression came out to be, we calculated was 2.9 KSI. So that means this is our plastic neutral axis. How I'm going to find that? I don't know this distance, so they call this distance X. Let's call this distance right here. Call this distance X. And we can see that this is not good here. So this is X, and this for this distance is going to become the whole thing minus X, right? Which is a 45 minus X. Now, this is for the top of the beam, not here. It should be a little shorter here anyway, for the girder itself. So I'm going to go ahead and calculate these two. I got one triangle here, one triangle here. Basically, I'm going to say the distance I'm looking for, it's going to be 0.36 divided by 2.9. This is just simple geometry here. X divided by 45 minus X. If you solve this equation very easily, and you're going to find out that your X or D, in this case, let's say this is the X, which I'm going to call the depth, and that comes out to this equation, if you solve it, is 45 times 0.36, divide that by 2.9 plus 0.36, and that comes out to 4.97 inches. Tensile force is equal, in here it's going to be 1/2 of FR times the area, which is going to become 1/2 of 0.36 times. This right here is a 16 inches. 16 inch times 497, and the distance is a 497. We just calculate that. So that will give us 14.3 kips. Because this is a KSI, that's a kip. Okay. So the required area for the steel is, for steel, because we need tension here, it comes out to be T divided by 0.5 FOY, and it said not more than 30. So we got 14.3 divided by 30, and that's going to become 0.48 inch square. So we got to add that rebar to the top. We can do one or two things. We can use number 4 rebar, 3 of them, or use we can use 2 number 5. Whatever, the area should come out more than 0.48 inch square. We know that anyway. It should be inch square. So that's why in here it failed, because our tension was less than or more than this here. So that's why it failed. So we got to make up for it by adding more rebar to it. That's not a problem. All right, let me erase this. We go to the final step. Number 15, we're going to check the flux flow resistance at the strength limit. Look at the AASHTO 5.7.3.1. And let me see if I can bring that up too. I want to find the dP, which is the distance from the pre-stressing steel. Let me write this down. Distance from pre-stressing steel to top of the deck. And that's going to come out to dP is equal. I got 45. And take out the 3.5 inch over there. And then plus 1 inch plus 7 inch. So that comes out to 49.5 inches. Okay. Then the next thing I want to find C. C is the distance between, I'm going to put it up there, between the neutral axis and the compressive force at the normal flux flow resistance in inch. And to do that, we have to go to this calculation right there on AASHTO 5.73. So the formula says C is equal. Let me write this in a different color so we can see it a little bit better. C is equal A area PS time FPU, and divide that by 0.85 F prime C beta time B plus K. All those is in a table, which I'm going to show up in a minute right there. APS and time FPU divided by dP, which is equal. I'm going to write it right here. And that's going to come out to 444. We had that time 270. Okay. And divide that by see, this marker doesn't work. That might work. I'm having a marker issue. So divide that by 0.85. Can we see it? Oh yeah. 0.85 time 7. We said we're going to use 7 for the concrete, or we can use 5. Either way, I'm going to use 7 for now because I changed my mind halfway through it. Time 0.8. Beta is 0.8 according to this spec. And then we have B is the width, which is at 7.25 time 12, which comes out to 87 inches. 87. And then plus 0.28. That is the K from the table of 5.7.3.1 time 444 time time, I'm not going to need this anymore, so that's going to be time 270, which is what's FPU, divided by 49.5. So C comes out to become 2.85. Okay. So now And if we use 5 in here instead of f prime c, if we use 5 right here, because at the beginning we used 5 for both of them, then halfway through we knew that it's not going to make it, so we may change it to 7. So if I use 5, that's going to come out basically 3.96 inches. So then we're going to say that's still less than 7 inches, which is right here. And our plastic neutral axis is in the slab. Okay? And now, because our plastic neutral axis is in the slab, then we have to use it as a rectangular section. So therefore, PS, according to the equation from AASHTO 5.7.3.1, it is FPU time 1 minus K time C divided by dP. And that comes out to 270 time 1 minus 0.28 multiplied by 396 divided by dP was 49.5. And that comes out to 263.9 KSI. So now we have that. We're going to calculate A here. A basically is the C time beta 1. And we had that 3.96 times 0.8. And that gave us 316 inch. That says a block. And then we're going to calculate the MU, which is basically phi time MN. And that's going to come out to phi time APS time FPS, and then time dP minus A divided by 2. Phi is a 1 here, so 1 time APS was 444. Then FPS was 263.9. And then dP was 49.5 minus A was 316 divided by 2. Actually, there's 317, there's 36, something like that, divided by 2. So now I'm going to end up with 4678 kip. Kip in, kip foot. Okay. Now let's find out our ultimate MU. Our MU is, you know that we did this many times, 1.25 time MDC plus 1.5 time MDW. Did I write those down? Oh, yeah. No, I didn't. Okay. MDW and plus 1.75 time ML plus IM. So that comes out to 1.25 time 457.7. The MDC also include the hunch, plus 409.9, and then one more, plus 110.4. Then plus 1.5 time MDW and that was 140.6, which I erased. 140.6, and then we have plus 1.75 time, it was 1208. It was up there, 1208.8. So that comes out to 35, 48.8, which is less than this right there, 46.78. Checks out. This was a short version of this problem. If you worked in a bridge design, you check a bunch of other stuff too. But this is how it's done. It was a lot of work, and if you like it, please give you a thumbs up. Thank you.